Hi, we are going to see today about resistors, inductors and capacitors in S domain. We have already seen part of this in our frequency response chapter, but we are going to see here from the context of Laplace transform. So let's start with resistors. Alright, with resistors we already know that any voltage that's applied on a resistor can be computed by the resistance R multiplied by the current I at t. So if we take the Laplace transform of these two sides, so in that case we have Laplace transform of V at t equal to the Laplace transform of R times I at t. So that basically gives us V at S, which is the Laplace transform of V at t, is going to be R, because R is a constant, times the Laplace transform of the current I at S. In other terms, if we are asked to compute, for example, just for pure resistance, then the inductance Z in Laplace transform is always going to be voltage in Laplace transform over current in Laplace transform, which would give us the resistance R. So in resistance term, because resistance is not frequency dependent, the ratio of the Laplace transform of voltage with Laplace transform of current basically gives you the same as the ratio of voltage over current in time domain. So with resistors we do not have that much problem. If you remember, in frequency domain, resistors were always maintaining their value because they are independent of frequency. Now it will be a little bit more interesting when we start with inductors. When we come to inductors, we know that the voltage across an inductor, where we have current I at t and a voltage of plus minus V at t here, for an inductance of L is given by V at t is always L times d I at t per dt. That was one of the relationships we have driven in circuits 1. So if we take the Laplace transform of this whole expression, what do we get? Laplace transform of V at t is going to be V at S, and that is going to be L, which is constant, times the Laplace transform of a differential. You remember, in Laplace transform we have said the law of time differentiation. The law of time differentiation tells us that whenever we have a deeper dt of a function f at t, if we take the Laplace transform of this guy, it's always going to be what? S times f at s minus f at 0, right? So applying that principle here, we will have the Laplace transform of d per di would be the multiplication of that's for inductance. Okay, inductance multiplied by S I at S minus current at 0 minus. So this value, if we are going to write it in terms of a circuit, it will be like transforming this simple thing into a transform of the inductor, and we have another value here, which is that part is L multiplied by S times Is. So if we have a current of Is flowing through here, then at that point we have S times L, and at this point we have plus minus I at 0 multiplied by Is. So we have this L times I at 0, which is going to be, that part is going to be the residue or the initial voltage. So an inductor in time domain is always going to be S times L time plus another voltage. So usually we take this initial value to be 0 in our previous frequency domain classes, but that's how an inductor is going to be transformed. So in this case, if we neglect, if initial value I0 is 0, then normally what do we have? V at S is going to be SL I at S, right? Which means V at S over I at S, which we call impedance Z at S, is going to be S times L. You are very aware of that value, right? You remember we used to call the impedance of an inductor as j omega L, because previously we used to equate S with j omega. But now, because S is going to be represented by sigma plus j omega, now we are simply using S times L. So impedance is replaced by S times L if it does not have any initial value. That's very important, if the initial value is 0. But if there is an initial value, then that will be S times L plus IS minus L times I0. So this is voltage and this is voltage, and that voltage is, this voltage is the residual voltage that we got from there. Alright, so let's see an example here. Just a simple example where we are having a circuit like this, plus minus, and let's say this is 3 times e raised to minus 8t u at t. Let's say that's the input, and it's connected to a circuit here with 1 ohm and 2 Henry in inductor, and we are asked to find the V at t of this guy, and we have current, of course, I at t. And we are given one more information where the initial current I at 0, the initial current I at 0 is going to be 1 ampere. So what are we going to do here is we are going to convert the value of, or the time domain, into a frequency domain. So when we convert the time domain into the frequency domain, we are basically applying Laplace transform. So when we apply Laplace transform, the source is going to be transformed from the Laplace transform of 3 e raised to minus 8t. You remember the Laplace transform of exponential function is 1 over sa. So in this case minus 8 will be plus 8, so we have 3 over s plus 8, or s minus minus 8, that would give us s plus 8. So that would be the Laplace transform for the source, and the Laplace transform for our 1 ohm is still going to be 1 ohm, because it's a resistor as we have seen it earlier, and the Laplace transform of our inductor, the inductor of 2 Henry, is going to be, the Laplace transform of our inductor is going to be, as we have seen it earlier, is going to have SL minus I0, right? Which is going to be, SL is, L is 2 Henry, so we will have 2S minus, we will have a voltage source of L times I0. Here we have L times I0. L is 2 and I0 here is 1 amp, so we will have a 2 volt source. So in that case, if I do the Laplace transformed circuit, then I will have the inductor, the resistor, and the inductor here, and then I will have that voltage source, right? Okay. So for the inductor, what do I have? I have a 2S. I have 2S ohms, and for the voltage I have minus 2 volt, and here for the voltage I have 3 over S plus 8. Okay, So that will be the transformed voltage, and we are asked to find this voltage here. V at t is the voltage there, which is going to be V at t there. So in order to find V at t, if we find I at s, then we are going to multiply I at s by this value here and subtract 2 volt from that. So from that expression, what do we have? V at s here, V at s, sorry, this is not V at t, this is V at s, because we are in time domain now, no more t. So from this expression, V at s is going to be current I at s multiplied by 2s, right, minus 2 volt. So the question is, what is I at s now? So in order to compute I at s, what do? We will just apply simple Ohm's law, right? When we apply simple Ohm's law, what do we find? We have here 3 plus, we have the sum of these two voltages, minus plus, plus minus, so the subtraction of those two voltages will be, it is just applying KVL. So applying KVL would give us to this circuit what? 3 over s plus 8, right, minus plus, plus minus, plus 2 is equal to I at s multiplied by that resistor here, which is 1 ohms, plus 1 plus 2s. So that will be our equation, from which we would find I at s is going to be 3 over s plus 8 plus 2 over 1 plus 2s. So what does that give us? When we compute that, it gives us, we are going to get, so we have already an expression for Vs, which implies Vs is equal to this 3 over s plus 8 plus 2 over 1 plus 2s, that multiplied by 2s minus 2. Alright. So when we simplify this, it would give us, if you just do some arithmetic, you will get this is equal to 2s minus 8 over s plus 8 and s plus 0.5. So using that partial fraction method, if you apply that partial fraction method, this has to be equal to a over s plus 8 plus b over s plus 0.5, where a is equal to that expression V at s multiplied by s plus 8 and computing s to be minus 8, and b is equal to V at s multiplied by s plus 0.5 computing s at minus 0.5. So if you solve that, that will give you for a value 3.2 and for b value minus 1.2, which means V at s is equal to 3.2 over s plus 8 minus 1.2 over s plus 0.5. So from this you will get, you can easily get the Laplace transform, the Laplace inverse transform of this and the Laplace inverse transform of that, in which case we are going to compute V at t. So from that you will get 3.2 times 1 over s plus 8 is basically e raised to minus 8t minus here 1.2 e raised to minus 0.5t. And in order to ensure that this is within the t greater than 0 region, we attach u at t. So this is going to be a voltage that we are going to get from that inductor. So one very important thing that we have seen here is inductors in time domain are going to be transformed into an inductor plus a voltage source. So the inductor is SL and your voltage source is I0 minus. So you have I at S here. So sometimes that initial condition will be 0, but in this case we have been given an initial condition of 1. So don't forget to apply that. Well, that's about inductors. Inductor of value L with a current of I at t and a voltage of V at t is always going to be transformed into a voltage of V at S, where that V at S is going to be the sum of an inductor and a capacitor running through an impedance of S at L plus I at 0. Alright, let's see about capacitors. Okay, capacitors, modeling capacitors is the same as modeling inductors. Well, the approach is at least the same. You remember when we had capacitors, we had some relationship on capacitors where the voltage, let me draw it vertically. Okay, if I have a capacitor here, we have said that for current entering into a capacitor at I at t, then the voltage here, V at t, with a capacitor C is represented by current I at t is always C dV at t per dt. You remember that, right? So this is capacitance. So the current is always represented by C dV at t per dt. So if we take just the same approach, the Laplace transform, take the Laplace transform of this whole side, what do we get? We will have I at S is going to be equal to C, which is a capacitance, multiplied by the Laplace transform of a differentiation by the time differentiation rule or property gives us S times V at S minus V at 0 minus, which is our initial condition. So that basically gives us a model of transformation here. So a capacitor is going to be converted into, because this is current, it's going to have that parallel path. So we have a capacitor here which has got current is coming from here, which is I at S. So that I at S is going to be the sum of SC, and we have another current source which is that V0, C times V at 0 minus, and that voltage for both of them is going to be V at S. So that current I at S here is going to be the sum of C times SC V at S, which is this side, which is on this side, and the other current here is going to be C times V at 0. Okay, so in this case, if we have that V at S, then if we apply, for example, the source conversion we saw in circuits 1, this can also be converted into a capacitor, and a current source in parallel can also be converted into a voltage source. You remember that, right? So we can have that where our impedance Z at S here is going to be 1 over SC, that's this part, and then we have a voltage here, V at 0 over S, which is. So in this case, we have a plus minus Vs here. So if you just compute Vs, for Vs you are going to have that value, right? Let's do that. So I have I at S equal to SC V at S minus S times V times or C times V at 0. So if I go for V at S, V at S is going to be what? V at S is going to be represented by I at S plus C times V at 0 over SC, which is the same as 1 over SC multiplied by I at S plus V at 0 minus over S. So this is the same thing we did here. That part is what we saw here, 1 over SC multiplied by IS, and that part is the initial voltage that we had on the capacitor. Alright, so if we do this, then our capacitor, we can solve for any of the voltages using this conversion. For example, if we have, say, plus minus a resistor and a capacitor here. So say we have a unit step, a 9 volt unit step, and a 3 ohms here, and a 0.5 farad capacitor, and we are asked to find this voltage, V at T. So what do? We convert first this into its Laplace transform. So the 9, let me use a red ink, so the 9 will be the 9 U at T, the 9 step function is going to be 9 over S, because we know that U at T is always 1 over S. So we have 9 over S, and the resistor is always going to be the same resistor, 3 ohms. Now the capacitor, if we are going to apply this division, what would that look like? It's going to be a capacitor here in parallel, which is 2 over S, right? Because 0.5, 1 over 0.5 is going to be 2 over S for capacitor. And then we are going to have, I'm just modeling this, right? I'm just modeling that. So we have here 1 over, for the current source here we have C times V, so in this case for C we have 0.5, and for the voltage we'll have a -1 current. So we have C times V at 0 because we are taking here an initial value V at 0 of -2 volt. So we have here -2, the voltage is -2, and -2 multiplied by 0.5, that's what we are going to do here. For C we have 2, we have 0.5, and here we have -2, so that's going to give us -1 amp. So that will be our circuit essentially, and we are asked to find what this voltage VC at S is. Alright, so if we just take a nodal analysis here, and this voltage is VC at S, so if we apply nodal analysis, what would that give us? VC at S over 2 over S plus VC at S minus 9 over S over 3, which is this one, plus 1, because it's coming, is going to give us 0. So solving there for VC at S, which is a capacitor voltage, is going to give us, if you simplify that, you would have -6 over 3S plus 2, and you are going to get -2 S minus 3 over S times S plus 2 over 3. So simplifying this expression would give you 9 over S minus 11 over S plus 2 over 3. So this is VC at S, which means we can have VC at T by just applying the inverse Laplace transform of that. That would give you 9 U at T minus 11 e raised to minus 2 over 3 T U at t. So that is going to be the voltage that we got from the capacitor. So in this case, the most important thing is replacing this capacitor. This capacitor was replaced by a capacitor and a current source which was defined by the initial value. Mostly in our previous frequency domain and circuit analysis classes, we have ignored the initial values. So ignoring the initial values would just give us a frequency transformed capacitor, but when we have initial values like this here, they are going to be added, and after that we just use whichever circuit analysis topic is going to be applied. Thank you. That will be all for this lecture.